Did you know that global data center power demand is projected to surge by an astounding 160% by 2030 as a result of AI workloads that run on energy-intensive GPUs? And that the current power grid is not designed for this short-term future. Welcome to SkyTech and Science. I'm Hector Duran, and today, we're tackling a topic that's often overlooked when we marvel at AI's capabilities, its massive and ever-growing energy appetite. As young innovators and tech enthusiasts, it's crucial for us to understand the hidden environmental and infrastructural costs of the AI revolution. You've probably asked ChatGPT to draft an email or tell a joke, right? You might think it's a quick, effortless task for the planet. But while a single query might use energy similar to an oven for a second, these interactions add up, and the larger picture is much more complex and, frankly, a bit dire for our planet. So, what makes these incredible large language models, or LLMs, so energy hungry? It boils down to their parameters, which you can think of as the internal knobs a model adjusts during training to learn patterns in data. The more knowledge you want an AI to have, the more parameters it needs, and models like GPT-4 are estimated to have over 1 trillion of them. These aren't running on your laptop, they live in massive data centers worldwide, packed with powerful chips called GPUs, or graphics processing units, which do the heavy computational lifting. All this number crunching takes colossal amounts of energy. Right now, data centers in the US already consume 4.4% of all energy, and that's projected to soar to up to 12% by 2028. The sheer scale is astonishing. While cloud computing previously saw flat power demand due to efficiency gains, AI workloads are exponentially more complex and resource-intensive. An AI server rack in 2027 will demand 50 times more power than a cloud equivalent from just 5 years prior, often requiring intricate liquid cooling systems to manage the intense heat generated by dense GPU clusters. Now, the most pressing bottleneck for AI progress isn't a lack of capital. It's the sheer power needed to fuel it. Global data center power demand is projected to surge by an astounding 160% by 2030. Measuring AI's carbon footprint, particularly for training these models, is incredibly challenging. Companies like OpenAI and Anthropic, who have the actual data, aren't sharing it. Training involves models digesting vast datasets over weeks, using thousands of GPUs and burning enormous amounts of energy, making it largely a black box in terms of emissions. Then there's inference, which is every time a user prompts the model. While training is a one-time intensive process, inference, over time, is expected to account for the bulk of a model's emissions because billions of users are querying these models countless times. But inference, too, is difficult to quantify. The environmental impact of a single query can vary dramatically depending on where the data center is, which energy grid powers it, and even the time of day. For instance, reasoning models, which explain their thinking step by step, consume far more energy than standard models because they process more tokens, bits of text to generate a response. To put it in perspective, using a 70-parameter reasoning model to answer 600,000 questions could emit as much CO as a round-trip flight from London to New York. And these numbers are likely even higher, as newer, more power-hungry chips like the NVIDIA H100 are being deployed. This brings us to the core issue, the structural mismatch between AI's rapid innovation and our aging power grid infrastructure, much of which is 40 years old. Our current grid wasn't designed for this future. Getting new power plants online, even natural gas ones, can take 5 to 7 years for permitting and transmission. While renewables like wind and solar are part of the solution, they can only provide intermittent power, and current battery technology can't reliably store power for the 24/7 baseload that data centers demand. This means a significant portion of the projected power growth will need to be met by new capacity from sources like natural gas, with nuclear power as a longer-term, reliable, zero-carbon solution, albeit with its own challenges like long lead times and high costs. Building this infrastructure is also incredibly expensive. A typical 250 megawatt AI data center costs roughly $12 billion. In fact, the hardware inside the compute equipment like GPUs can cost 3 to 4 times more than the physical building itself. This makes financing very complex for developers and lenders alike, especially given the rapid pace of AI innovation and the risk of hardware becoming obsolete. To get around grid limitations, some operators are even going behind the meter. building microgrids directly on site, or co-locating facilities near power plants to act as their own power suppliers. Goldman Sachs research estimates that about 60% of data center demand growth needs to be met with new capacity, likely powered by 30% natural gas CCGT, 30% natural gas peakers, 27.5% solar, and 12.5% wind. However, wind and solar power only function when the weather cooperates, and battery technology is currently unable to store power long enough for reliable baseload power. Nuclear power can be a good solution to cover the energy demands, as it offers reliable, 24/7 zero-carbon baseload generation. But it is considered as a long-term solution given its high cost and longer time to deploy. That's all for today on SkyTech and Science. Thanks for tuning. If you liked what you heard, share it with a friend, follow the podcast, and let us know what topic you'd like us to explore next. I'm Hector Duran, and I'll catch you next time as we explore the cutting edge of science and technology.